Hi everyone, this is Vidette Makes, and tonight is ValpoHacks, our meetup, and tonight Adam is going to give us a presentation on a project that some of our ValpoHacks students have been doing, and Adam is a software engineer, and he is president of Vidette Makes. I'll give you the mic now, virtual mic now. Adam?
Okay, cool. So we've been working on this project. And so for anyone that doesn't know, um, we've partnered with Valpo University to basically make what we call a filament extruder. The point is, or the program that we want to start is because Vidette wants to do engineering-based projects that impact the community in a positive way. What we would like to do is take organizations or partner with organizations that have 3D printers. And so you think like schools, boys and girls clubs, homeschooling groups, libraries, and even individuals that have 3D printers, and you think, okay, I'm going to print something, but maybe it takes me 3 or 4 or 5 times to print the right thing or to print it well. And so the rest of that, the old prints, they're trash and they'll go into landfill. So what we would like to do is create a program where we take the waste plastic from 3D printing in our communities, and we grind that up and we can melt it and extrude it into filament again, and it can be reused. So we partnered with VU to basically build the most complicated piece of equipment that we would need for that. So if you think about plastic, plastic in its raw form, in its manufactured form is little pellets, and you take those pellets and you melt them and you either squish them into a shape or you mold them into a shape or you extrude them into a shape, which is what we're doing. So we take the waste. So to get it back to that, we need to take the waste plastic, we need to grind it up, and then you need to get the water out of it, which sounds kind of strange, but it does need to be really dry. So you need a grinder, you need something to dry it, which could be a food dehydrator, and then you need an extruder. And of those pieces of equipment, the extruder is the hardest part to build, or at least an extruder that can make something with a uniform thickness like a filament, like a plastic filament needs to be. So we partnered with Valpo University, and we told them what the project was about, and they formed a senior design project for the engineering students. And so we had a few engineering students that basically spent their school year designing and making a machine for us to help us with this project. And so what you see behind me in my garage is half of that machine. The other half is off to, I don't know if that's the left or the right, but off to that side, there's another half of that is just as long. And so what I'll share with you today tonight is a little rundown of what the different parts of the machine are, how it works. I will not turn it on today because it needs some adjustments I need another table so I can set the whole thing up. But this is the intro, and then at a future ValpoHacks, we'll get the thing running, and I'll show you what it looks like when you actually make plastic. So basically, starting on this side, so there's a motor's there, and then this is a gearbox that reduces the speed of the motor, increases the torque, and it ends up turning this screw. There's a shaft here that goes into a barrel, and the barrel has a heater. This white thing that's wrapped around is a heater, and inside of here there's a screw, and the screw basically think of like if you've ever made pasta or like a meat grinder or anything like that. It's got a little screw inside that kind of pushes stuff. That's what's going on, or like an auger in a grain silo. But anyway, so there's a hopper here. You put the plastic on the inside. There's a little, this is a plexiglass window, so you can see how much plastic is in there. It falls down and gets melted here, gets pushed into the barrel, and as it goes in the barrel, the screw compresses it as well. And so it's getting hot and compressed. And then at the end, there's a little tiny hole where the plastic squishes out. So think of like, it's basically a really, really fancy, really big hot glue gun, where instead of a trigger, you've got this screw pushing stuff. The big box on that side is some of the control circuitry and a lot of the electronics to power the heater and the motor. So there's a lot of big MOSFETs in there, big transistors that power these heaters. The plug, which you can't see on this video, oh, maybe you can. You'll notice this is not a normal household plug. This has the ground prong, that's the circular one on the bottom. And it has one blade here that's vertical and one blade that's horizontal. And that doesn't plug into a normal household outlet. This is for a higher current outlet than normal household outlet can provide, which is why it's in my garage, because my house happens to have one of these outlets, but it's in my garage. So that's why this is in my garage. But it takes a lot of current, it takes a lot of power for the motor, but also mostly for the heaters. There are 3 heaters here. One is the one that's wrapped around the barrel, and there are 2, you see these red wires here. There's a heater, there's 2 little cartridge heaters on the front where this squarish piece is, and that's the nozzle. So that gets a different temperature, and then there's also, you'll see it, if you can barely see, there's a white wire here. So there's a thermocouple here, and there's another thermocouple taped up here. And so those are used to monitor the temperature of the barrel and the nozzle. Let's see, if I go over here and turn this way, you'll see 2 little black boxes here. These are temperature controllers. So these use sophisticated software called a PID loop, proportional integral derivative is what that stands for. And if you ever take a controls class, and like a software controls class, which I have not taken, so I don't know I don't know the intricacies of the math, or I don't know the formulas for the math, but basically this uses calculus to figure out when to turn the heaters on and when to turn the heaters off to maintain whatever temperature you want to maintain. So it's not just you push a button and the heater just turns on and it stays on, or else it would get too hot. Instead, these will turn the heaters on and off as needed to keep a steady temperature that it's set to. And the reason that's important is every plastic melts at a different temperature, and every plastic burns at a different temperature. And if you get the temperature wrong, then you could burn the plastic and ruin the material. You could also emit some really toxic fumes. And so for every type of plastic, we have to set a different temperature. And right now, we know the temperature for PLA, which is one of the common plastics used in 3D printing. We have to do some more research and some experimentation to figure out what the right temperatures are for other plastics. Let's see, other things that are interesting. So this shaft right here, This is a coupler that allows some flexing in the shaft. So if this is not perfectly level to the motor, that keeps it from breaking. These 4 screws are used to make it as level as possible, but that's what that's for. You can see all these wires here. You can tell this is not like a finished product. So one of our ongoing tasks will be to make this a little more robust, kind of make the wiring a little nicer. The yellow and red device over there, that's an emergency stop button, which right now also functions as the power button. So you pull out on this like that, and there's a yellow, you can see a yellow ring around the handle to indicate that it's on. And if something were wrong, like let's say someone was getting burned or shocked, do that, and it turns it off. Let's see. All right, so now I'm going to bring the other part of the machine over and show you the other part of the machine. Grab it from the wrong side. Okay. Okay, so I don't know how easy that is to see, but okay, so when this whole machine is set up, this whole long silver piece will fit on the end of the black piece. So it's really long. And what will happen is, so at the end of the nozzle here, you have this string coming out. Or this plastic that's kind of gooey, hot. Think of a hot glue gun and the kind of that consistency, but it's basically a big hot glue gun. So once the hot plastic comes out, we need to cool it down, and then we need to pull it to make the right it the right width or diameter. So think of like if you've ever gone to the fair and seen taffy being pulled, as you pull it, it gets thinner. Same kind of thing, same kind of deal. The more you pull on the plastic, the thinner it gets. And that's how we control the diameter of the plastic. So think about a 3D printer. A 3D printer takes a specific diameter of plastic that it needs. And so we want to try to control that diameter to get a filament that can be used in a 3D printer. So once the plastic comes out, it will, if you imagine this is on the end of there, right here on the end, you'll see two little, they're not quite computer fans, but they're close to that. This one blows down and this one blows up. And so the plastic would kind of come in here and get blown on by these fans to cool it off. From there, it's hard to see with the wires, but it just lays in this groove and goes through this groove, and then it reaches this this device. And what happens here, and I need to get the micrometer that fits here. Basically, there's a micrometer that fits right here, and this moves up and down, and it measures the thickness of the plastic. So this measures the diameter that we're currently extruding. Once it goes through here, there's a little slot, the roller here, and then there's a little slot. Then this is our spooler. And there's a motor on here that is controlled by an Arduino, and we can control the speed of this motor. And basically we would take a spool. I'll just go ahead and put a spool on so you can see what I'm talking about. take a spool like this and stick it on here, and then screw it in like that, which I won't do to save time. But basically, this goes here and it winds the plastic up. And the speed at which you wind is how much force you're putting on the plastic, which stretches it out or doesn't stretch it out. Let's see, what else? The green boxes over here, you can barely see them. So these two green boxes are Arduinos and circuit boards that control the electronics. So there is basically there are knobs here to control the speed of the motor and the speed of the spooler. And eventually, we'd like to be able to take a reading from the diameter from this micrometer and use that to control the speed of the spooler so that we can control the diameter of the plastic. One more thing to show you. So this is what plastic looks like. See, I'll try not to spill this everywhere, but there's these little beads. This is new plastic, so it's never been used before. They're kind of these, I don't know, they look like little tiny beads that you'd put in a child's necklace maybe, but they're just white. This is raw PLA, that's how it comes. So anything that you buy that's plastic started out probably in this little bead form, and it was used in a machine to make it the shape that it needed to be for the product you bought. Let's see. I'm not going to try to put it in the bag again. So I'll put it in the hopper. There you go. Oh, you can't see this, but there's the students put a little grate on top so that no one would get their hand caught. So that's the raw plastic. When we're actually recycling, we will mix it with this. This, trying to spill this on my laptop, that is ground up plastic from a 3D printer. So this is PLA, the same kind of plastic that was in those raw pellets, but this is the waste of a 3D printer in a library. I think this is from Chesterton's library, and they saved this for me, and I was able to get a plastic company to grind this up for me, and we used that, or we gave that to Valpo University to experiment with. But this is the kind of thing that we will get from, or that we will end up with from the community, and we hope to recycle. So when we do this, we'll take this stuff that we grind up. This is the old plastic that we want to recycle. We'll mix that with new plastic and then feed it into the machine. You can't, I'm going to dump this back in the box. I have a big old box of that. Actually, I should show you the box because it's fun. Here's my big old box of plastic. And anyway, so you have to mix the old plastic and the new plastic. And the reason we have to do that is because plastic is, it's really not a very environmentally friendly material. And one of the reasons it's not great for recycling is that you can't just melt it and reform it over and over. You kind of have to, if you want to recycle it, you have to mix in old and new together. So probably something maybe like 25% of our plastic could be recycled, and something like that. We'll have to experiment to see how much recycled stuff we can use, but you can't just use old plastic. You have to mix in some new. Anyway, so once all that, once everything is in the hopper, all mixed together, you extrude it out. It ends up looking something like this. So this is, I have several spools here of plastic from the VU students as they were experimenting with this and getting this to work, and trying to figure out in the process of building the machine, they extruded several spools of plastic, and this is one of them. And so it's hard to see you can't see it in the video, I'm sure, but there is in this spool, you probably couldn't use this in a 3D printer because the diameter of the plastic is not, I think they said it was a little, when they tried it, it was a little too thin, so the printer couldn't grab it. And also this one has quite a few breaks in it. So there's a piece of duct tape where they taped the end together so the machine would keep going, because they were still trying to figure out how it was working and stuff. But they did get it working. And like it's at a point where with some adjustments and some cleverly written software, we could probably get this to work rather nicely, where my hope is if we got a nice software loop going, we could actually get this to adjust the tension automatically to maintain our thickness. But yeah, so that's the intro to the machine, and the which will hopefully be the first of several demos or many demos, and hopefully this will be the only one that doesn't have moving parts moving. So hopefully the next time you guys see this, it'll actually be cranking out some plastic, and maybe have a little less of a wiring mess. All right, so I think that's the end of our presentation, or the end of my presentation, and I hope you enjoyed it very much.
Does anyone have any questions for Adam?
I do. That was awesome, Adam. One question I had was, and this may be silly, but if you look at the kind of the spool you just showed from VU,
yeah,
one of the examples of the recycled plastic, I noticed the plastic was clear, I think, in that situation, and then the recycled bits are all colored. So I guess when they're melted together, what determines the color? And do you end up with like an amalgam of colors, or do you end up with...
So I should have clarified this. What I showed you, this spool, this has 0% recycled plastic in it.
Okay.
This is just the clear virgin plastic.
Gotcha.
When all the plastic is mixed together, I'm expecting it to be kind of a gray.
Okay, that's what I figured. It would be some sort of like grayish brown or something.
Yeah, it'll be whatever. I mean, if we had just a bunch of blue and we mixed it with the clear, it'd be like blue. You know, it would be whatever it's mixed in with. I'm thinking it'll be some sort of light gray.
And then another question. This is more of two things. One, I think the schematics, I guess, or the work for this is all open sourced on GitHub.
Yes, it is. Yeah, you can see the. I haven't delved into it like super deep, but I know there is. There are a couple PCB boards that are using KiCad. So that's all open source in there. The design files are there. There are several different Arduino sketches. There's an Arduino Mega in here and an Arduino Uno, I think. And the sketches for those are online. And what else? The CAD files for all the pieces that they've machined so like this is a 3D printed part. This is a 3D printed part. There's a bunch of 3D printed parts here as well. They are all online as well in our GitHub.
And then my final question right now, if I might have another one in a minute.
Wiring diagram too. I really hope there's a wiring diagram. That'll make one.
Do you have an idea of the general cost of components for this? I mean, maybe ballpark.
Yeah, there's a bill of materials in there too.
Oh, is there? Okay.
Yep, there's a bill of materials.
I looked at it.
Yeah. When we initially talked to the VU students, what we said is this is going to be an open source design. So we want this to be something that we can replicate and that we can maintain, and that someone else could replicate if they really needed to. So yes, we said we needed schematics, we needed CAD files, we needed PCB files, we needed code, and we needed wiring diagrams. I think the only thing they didn't do is an instruction manual. But
no, I love the open source.
Pretty good notes as we watched them use this. So we did actually see this running, and they showed us how they get it together. I
love the open source mentality. Yeah. It's very cool.
Like already I'm thinking like, all right, I can change this wire a little bit. Like I know like one of the things that is like probably the most difficult thing about this machine is getting started. You have to take you don't want to use your fingers because it's really hot, but you got to take the plastic and thread it through this. And I think one thing that would make that a lot easier, so you take like little pliers and kind of work it through. One thing that would probably make it easier is right here. In here, there's little holes that it goes through, and I think if these were slots instead, you wouldn't have to thread it through like a needle.
Gotcha.
So it's like little things like that, but I'm already thinking like, oh, that could be a little better, that could be a little different.
Yeah, it's cool because it's open source, so you could theoretically make the changes or someone to change it. And
yeah. Also, as a little bonus, this spooler is actually on top of 4 strain gauges. So they said as a bonus, we put these 4 strain gauges here. If we wanted to, in a future upgrade, you could actually have the machine measure the weight of the spool and determine when it's done to stop.
Oh, that's cool.
Which is kind of cool, but it's not implemented yet. Right now, the wire's just coiled up. But I was like, that's kind of neat. Like we had talked about that in one of our meetings, and they said, well, we'll throw it on there, but possible future upgrade.
Awesome. Great work, man. This is really cool to see.
Thank you. Like, I'm pretty excited about it. And I think I need to send a shout out to Dan Blood, who's professor at VU who worked with the students. He was their supervising professor and the one that worked with his team, and he did a great job of, he was the one that recommended the screw and barrel for us, because I'm a software guy. I don't know how plastic works, at least not by trade. And he did a lot of work. Like he's, I think, been kind of the pioneer behind this, and then we just kind of pushed it a little bit more.
That's cool.
Who are the students?
Oh,
give them the credit they're due.
Right. I don't have their names all in front of me. If you give me a minute, I can find it.
All right.
But yeah, actually, what I'd love to do is get the our website could do a shout out to them, because I have in our first meeting with the student, or my first meeting with the students, they gave me a little bio of each of them and a picture. We could probably put that on our website.
Yeah, we'll have to talk to Heather about that. I'm sure we can make that happen.
Yeah.
But yeah, it looks like they put in a lot of work. I don't know if they even know how many hours they've done collectively, but
let me pull this up here. Maybe I can do a screen share with their names and bios.
I can, while Adam is looking that up, I can throw in a little detail. So this is the courses, plural, that they're in doing this is constructed as 2 3-credit college classes. So this is, and 3 credits is several hundred hours of commitment. Like that would be the normal expectation in the world they live in. So this is probably 600 hours times 5 or 6 students. It's probably about right. So yeah, they gave it a lot of time.
Here we go. All right, I've got it. Let me figure out how to share.
So we're
Oh, wait.
talking tens of thousands of hours collectively.
Share screen. Here we go. Oh, wait. It says host disabled participant screen sharing.
Oh no. Let me fix that real quick. Okay, go ahead and try it now.
All right, let's see what I can do. Here we go. Share that. Here we go. So here's our, so when VU does a, when VU does a senior design team, they actually, they do it as if the students are their own little company, like a startup. And so everyone's got a C-suite title. So like one will be the chief executive officer, another student will be the chief communication officer, and that's the one that emails me all the time. And another one is the chief financial officer. So it's just actually kind of cool. But anyway, so Connor was our CEO, mechanical engineer. Do you want to read these or?
I mean, a quick TLDR.
Gotcha. So we had Connor and Manib were mechanical engineers, and let's see. So you can kind of see they had different responsibilities. So Connor's responsibility was basically delegating tasks and coming up with schedule, or delegating tasks and handling just the team dynamics. COO was the scheduling, and Nicole did the budgeting, and I think she did the 3D printing as well. And then I think John and Alec were, oh no, John was the computer engineer. There was another computer engineer. Alec was mechanical, and there's our other computer engineer. Oscar was computer engineer, which Oscar was the one that I communicated. He I got to know the best because he was the one that he's chief communication officer. So he was the one that his job was to email me because I was considered the sponsor of the project. Or really, like Vidette Makes was considered the sponsor, but I was the liaison kind of. So he would email me, so I got to know him fairly, or more than the others. But yeah, that was our team. 1, 2, 3, 4, 5, 6 of them, right? Yeah. Yep. So that's the team, which they're all graduated now.
Yeah, I did the math. I did a lookup as to what sort of normally expected. It would be we got about 1,000 hours of time out of the team.
Yeah, which is, we could get together and build this if we really wanted to, but it was such an educational opportunity. Like, why not have the kids do it? And actually, it was Dan Blood's idea. I came to him and asked initially about purchasing a machine. And he said, well, why don't we just build one? Or he recommended, he said, it'd be better to build one than purchase it, because what if the company goes out of business or something? And I was like, who has time for that? And then he came back to me and said, I've been thinking about it. Maybe we should do a senior design project. And I was like, yes, let's do that. And so the students did a great job, and probably cost less than buying something anyway. Yeah.
It's also worth throwing in there that along the way, they're required to practice a lot. Like, this is the sort of the classic capstone experience for them. So they would also, in addition to actually building the thing, they had to design it, they had to lay it out. They did some testing along the way to see what worked, what didn't. Like, they went into this.
They determined the temperatures that we needed for this.
Yeah. They also had to explain it and budget it.
Mm-hmm.
So they had to build the timetable.
Right.
Sometimes it's a little bit of a work of fiction for most senior design projects, but they do a lot of additional sort of traditional office-y kind of things along with, and then they actually have to show it off. So we actually have their design poster and some other stuff too.
Yeah. I should show the design poster. I have that. Let me grab it. because I think that poster is super cool. Can I show it? Slide show from the game. Hey, there we go. Oh, shoot. All right, and share screen. All right, this is hard to share PowerPoint on a single. Here we go. Share. There you go. There's the fancy poster that they came up with, which has our logo on it. All right, I'm gonna be right back.
Neat. Filament Extruder.
So I'm hoping that, you know, as the university loosens its rules for COVID, this is actually in the hallway. This is not only just, you know, a document, it's physically printed, it's framed, it's in the showcase hallway for the College of Engineering.
Yeah, Nick showed me. It's like hanging up on the wall in one of the buildings.
I think we had a photo op, actually. I think we had a photo.
Oh, yeah. Mm-hmm.
Another question, Adam, because you mentioned with Daniel, maybe you missed it, but do commercialized versions of this exist, or is this like a brand new creation?
Sure, yeah. So, okay, it depends on what you mean by that. Oh, also, this is the piece I didn't show you earlier. This is a micrometer. So, thing comes up and kind of see it's measuring the.
I don't know that we can see you since the screen is
hold
shared.
on, stop share. Here's the micrometer. It pushes up like that. It fits right here, like that. So filament presses up against that and measures it. And for those who are technically minded, there's a USB port here.
I was gonna say, does it go through the USB port and stop it if it's wrong, or?
Okay, so this is the interesting part. So this can interface to a computer or to something. So the idea is you take this and get a readout of it and then use that to determine the speed that you extrude at or that you spool at. But I was looking this up. So there's a USB port here, but it's not actually USB. I think it's like I2C or something. So it's like there was a big warning on the manufacturer's website that said, do not plug this into a computer. So that was kind of annoying. But the students didn't get to that part. So we have to do that, which is that's okay. I do that all the time. That's my job. Also, that was there's a little bracket here that I broke that holds this in, which is why it's not here. But this whole piece is 3D printable, so now I can, so we can replace that pretty quickly. But anyway, okay, your question, Cameron, was commercially exist. Hey, we're back. Okay, Cameron had a question about, is this something that commercially exists? These kind of machines do. So in the course of manufacturing plastics, like, yes, there are extruding machines that exist. And also there is an open source version of an extruder similar to this. There's a website called Precious Plastic it's a European company a European nonprofit corporation that put together a series of open source plans for machines to recycle plastic. And one of their machines is an extruder. So you can find machines like this in plastic factories, like factories where plastic pieces are made. You can also find, if you go to the Precious Plastic website, you can see their open source design, which is kind of similar to this. The difference with theirs is they're not trying to make filament, so they don't have a way to wind the plastic as it comes out, and they don't have a method of controlling the diameter of it. So that's special to this machine. That's what makes this one special, is that we can well, eventually this one will be able to do that. As far as, but if you're talking, okay, so that's the machine. As far as this kind of project, the answer I think is no. Plastic's pretty difficult to recycle, and it's pretty difficult to do it cost effectively. Or wait, no, I take that back. I think there are a few companies, if you Google recycled filament, recycled 3D printer filament, there are a couple companies that will take plastic waste and give you recycled filament, or sell you recycled filament. And actually, I think most of them, it's been a while since I did research, since I looked this up, but I think the ones that I found, you could purchase recycled filament, but there really wasn't one that took your waste and then gave you recycled stuff. I think it was more like, we'll sell something that's such and such percent recycled, which is fair, because you can't get 100% recycled plastic. So sort of is the answer. Does that answer your question?
Sorry, I was muted. Yes, it super answered my question. That's super interesting.
But yeah, this is so, just to add to that, this is not something that will probably ever be financially lucrative. It's not like we're going to get tons of plastic and then just for free and then sell it all, like make filament and then sell it all. That's not quite how it works. I mean, we will get like scraps of plastic for free, but you do have to purchase new plastic to mix in, right? So you don't just get your raw materials for free. And then the stuff that we print or that we extrude is probably some kind of gray, stuff. So it's not like there's going to be like a bunch of different colors to choose from. We're not going to replace anybody's supply of 3D printer filament. So whatever school, or let's say the library, decides they want to use some of our recycled filament, they'll probably still have to buy filament elsewhere too. So this project is much more educationally lucrative than it is financially lucrative, and also more educationally lucrative than it is environmentally lucrative, because we're not saving vast amounts of waste. We're just doing 3D printing waste, which is still waste, but really it's about showing kids and students and community members, this is the whole life cycle of a product, from design to manufacture or 3D printing to end of life and recycle.
And I personally think it's a really cool lesson on recycling and just how it happens in general. Like, I think it's a really neat overarching it's really neat to see it happen on 2 6-foot tables length worth of equipment.
Right. Which is right now 1 6-foot table. So if anyone has a 6-foot table, they don't need another 6-foot
no,
table.
I think it's really cool to see it happen right, like, you know what I mean, right in front of you. It's very quick,
right.
Very easy.
It also is a really awesome illustration of like why reading the label on your recycle bin really matters. Like, this thing does stop pretty much if the wrong kind of plastic ends up in it. Like, we don't have a solution for that. Like, that's quite hard.
Okay, so I have a story. So
did you plug it in?
No. Okay. Did I? Okay, so the shredded plastic that I showed you, the colorful stuff, so that came from a couple different places. The bulk of it came from Chesterton's Public Library. So thank you very much to the Chesterton Makerspace. But some of it came from a couple other different individuals as well. And one person that donated to us wasn't super careful, and there was a little chunk of metal in with their plastic. And so when we ground, so I went to this, there was a company in Chesterton, an injection molding company, that offered to let me use their grinder to grind all that plastic up. And the person who was working with me took the whole box, dumped it into the grinder, and that little piece of metal, the machine still works, but it made some really nasty looking gouges in the teeth of that grinder. So that was kind of the first rough lesson of, if you want to recycle anything, it's got to be clean and it's got to be sorted and it's got to be pure, or else things go really badly really quickly.
Were there any more questions?
I like Everett's question. I haven't asked because I don't have more plastic yet. Everett asked if I'm allowed to use that grinder again. I haven't asked because don't have more plastic yet. But eventually we will either need to purchase a grinder or have an agreement with someone who has a grinder, either that injection molding shop in Chesterton or another business, which I'm not super worried about. I think as word of this gets out and more people get excited about it, I think there's a number of different businesses in Daniel's making comments about Elon Musk, but I think there's a number of different businesses that that will probably get really excited about this and want to help us out.
And I think you mentioned, Adam, but just to go back on it, the percentage of recycled plastic to new material is probably somewhere around the 20 to 30%.
I think so Nick and I wrote down notes from the students, and I think it was something they thought it was 25% was about the best we were going to do. But I don't think they knew a firm number.
Gotcha.
We'll experiment with it. I think what we'll see is mosquito. Actually, you know what? I haven't tried it, so I guess I shouldn't say what I think will happen if we put too much recycled stuff in. But we'll find out. It may have difficulty melting or difficulty melting together.
Sure.
You know.
All right. Well, if that's it, I think I'll wrap it up and stop the recording. Thank you, Adam, for showing us this machine and giving us all this information. It's a fantastic project, and
My pleasure.